Welcome everyone to day 2, our final day of the National Alzheimer's Coordinating Center 2021 Spring ADRC meeting. My name is Hannah Rosentrader and I'm a program operations specialist here at NACC. I'm very excited to introduce today's director's session, which will be from 11:15 a.m. to 1:45 p.m. Eastern. But without further ado, I would love to hand things off to Andy Saykin, who is the chair of the ADRC Executive Committee and the director of Indiana ADRC. Andy, take it away.
Thanks very much, Hannah, and thank you all. It's really great to have this opportunity to get together, even though it's virtual. So I guess I'm your virtual chair, having done the same thing for the fall meeting. It's been a really challenging time for our whole community, and it's been so impressive the way everyone in the Alzheimer's research community has come together in a collaborative manner to cope with all the changes required over the pandemic year. And fortunately, we're starting to see the light at the end of the tunnel, and things are looking better. Things are beginning to get back to at least the new normal operations in many of the centers. So there's been a lot of progress made and a lot of, as I mentioned, collaborative efforts to find ways like remote assessment to cope with what we've had to deal with in the past year. It's a really exciting time in Alzheimer's disease research, and I think it's really nicely reflected, by the summit that was just held, and I'm sure you'll hear more about that momentarily, as well as a very exciting day yesterday and this morning from the imaging, biomarker, and administrative cores and the research education from all these terrific trainees. So it's just really been off to a great start. I want to thank NACC for all of the efforts to put this meeting together, which has been truly impressive. And as I'm sure you've noticed, there are a lot of new faces. There've been there's real invigoration of new folks at NACC as Bud has built the team, and I think the production standards and everything else have just gone up and up, and it's really impressive. So I want to thank all of the team members who put this meeting together, and as well as my fellow executive committee members, Oscar Lopez and Suzanne Kraft, and then the NIA leadership and NACC, who all were involved in putting this together. So now I'd like to go to the NIA portion of the meeting and introduce Dr. Richard Hodes, director of NIA, and that will be followed by the other NIA leaders. Thanks. See you shortly.
Thank you, Andy. And I'd like to begin by thanking profoundly and congratulating the way the center's program and all of you have managed to function during this most challenging year. It's a dramatic testimony to how effective you are and the value we certainly place in this partnership. Can we move to the next slide, please? I'd like to begin with an update of some of budget appropriations events. Next slide. So for FY21, the fiscal year in which we are living, the overall appropriation to NIH was some $42.9 billion. There were several areas, again, which received targeted funding, and among them, most relevant to us, of course, is an additional $300 million increase this year for AD and ADRD to a total level of funding of approximately $3.1 billion. The NIA budget now is increased to some $3.9 billion. Somehow now becoming the third largest institute by appropriation at NIH. And there is an increase in addition to this targeted funding to the base, which allows us to expand aging research across all of our divisions. Next slide, please. COVID. During the COVID times, there have been to date some $4.8 billion in COVID funding to NIH. Now, none of that has come directly to NIA or to Alzheimer's research. The largest component, as you can see illustrated here, is to the NIH OD, Office of the Director, and that's funded a number of trans NIH initiatives in which we have certainly functioned. And some of you have been involved in supplements and programs. NIA leadership has been an important part of a number of the activities, both around the acute pandemic and the studies currently ongoing looking at long-term sequelae of infection. The next slide, please. This shows you the increase in appropriation to NIA over years, as shown in the upper line as current dollars, the bottom is inflation adjusted constant dollars, and continues to be a remarkable testimony to the confidence that the nation really in congressional appropriations have had in the work that we're able to do together, its importance and the progress we are making, with an increase of about $1 billion as recently as 2016 to nearly $4 billion now. Next, please. This just shows you a reminder of the year-over-year increases that have occurred, the large, very large increases happening annually from 2016, and including the $300 million appropriation that we received as of December 27th, 2020 for this fiscal year. Next, please. These data are just showing from 2015 through 2019. It's only through 2019 because of as a technicality, there's certain data we don't release until the president's budget for the next year has come. But I did want to illustrate the magnitude of increase over these years, some fourfold or so, and to illustrate that it's been distributed over Alzheimer's disease as well as each of those designated relative dementias that are a part of the targeting ADRD appropriation. So quite amazing, a fourfold increase, and with this year's appropriation it'll be greater still. Next, please. So this year, we're of course all wondering what's coming in 2022. There have been no draft bills released from the Senate or House at this time, so not a clue from Congress about what there is to come. The president's so-called skinny budget was released last month. Skinny because it really is just an outline. The full president's budget still not yet released. It proposed a very substantial increase to $51 billion for NIH. Of that $9 billion increase over this year, $6.5 billion was for establishment of ARPA-H, Advanced Research Projects Agency for Health. This is on the model of DARPA and some other ARPAs that are in existence. And notably in the skinny budget, the very brief outline documented that the efforts of ARPA-H would focus on cancer and other diseases such as diabetes and Alzheimer's. So certainly encouraging at this level to see Alzheimer's referred to in the president's skinny budget, in particular in this ARPA-H initiative. And we are on a budget through September 30th, as usual, hoping to have a budget for 22 by then, but accustomed to the fact we may be working with continuing resolution, but this will become clearer over the next months. Next, please. Policy updates and some spending information. Next, please. So pay lines, we once again have some very substantial differences in the so-called general pay line versus that for ADRD targeted research. And this is resulting from the targeted congressional appropriations. So if we look first at the ADRD pay lines, once again this year we'll have a 28th percentile for as a pay line for percentile of applications, 31 and 33 respectively for NI, that's new investigators, and ESI, early stage investigators. But I just point out to you that the very challenging pay lines we have in the general pay line are quite a bit lower for our initial, at least, allocation in the general pay line, the most common under $500,000 awards, 8th percentile with 11th and 13th for NI and ESIs. We may be able to adjust this during the course of this year, but not by a great amount, not nearly as much as we'd like. Of course, we wish we could support general aging research to an extent comparable to what we're currently able to support for AD and ADRD research. Next, please. Some of the other pay lines that refer to important mechanisms such as program projects, other NIA reviewed non-percentiled, where here these are the priority scores that we show you, as well as for the important areas of career development and fellowships, where we're determined to maintain the stream and recruitment of investigators into AD and ADRD research. Next, please. As you know, I think we have attempted to make the most of the investment in AD/ADRD research by looking at the capabilities of the other institutes across NIH to contribute. And so we've had a number of programs in which we have supported research to investigators supported by other institutes with the use of the funds that come to NIA for AD/ADRD targets. One of those programs illustrated here, yet again in FY20, was a supplement program. And as you know, this allowed awardees with other NIH institutes whose research was not categorized as AD/ADRD, but wanted to propose supplements to their research within scope that would bring their work into relevance to AD/ADRD. You can see the numbers of such supplements funded in FY20 across a number of institutes, NINDS the most frequent, but you can see across nearly all the institutes at NIH, a total of about 312 supplements and $107 million in total cost. The next slide, please. This is to illustrate for you in terms of research investments, the dollars in competing awards, RPGs, and clinical trials that have come over these past years, as expected, increasing as the appropriations have increased. Next, please. Success rates, which are another metric of our ability to fund the applications that come into us, are shown here. The upper line for NIA, the lower in blue for overall NIH. And you can see that, as expected from our pay lines, as noted, the success rates have been higher for NIA overall. This in large measure, of course, due to the AD/ADRD success rates. And the gap between NIA and NIH, interestingly, is narrowing. Our projections, of course, very much depend upon what happens with these additional targeted appropriations. Were they to continue, we would certainly be sustaining the kind of pay lines we've had. But just in terms of sharing reality with all of us, should those extraordinary increases cease to occur, and should we continue to grow at the more modest rates of other areas, we'll be again facing some of the more challenging priority decisions, and I'll be working with all of you and arriving at those. Next, please. The NIA, as all of NIH, had a program of urgent response to COVID-19, SARS-CoV-2, while supporting pre-pandemic mission-critical activities. And we, along with other institutes, issued then a supplement program. The initial supplement program expired in December, but NIA continues to encourage applications and to review them for COVID-19 related research via all of our normal channels and mechanisms. Next, please. We recognize that a particularly vulnerable group through this pandemic has been that of early stage investigators and trainees, those at career development stage. And so we've paid particular attention there and have offered to F and K awardees whose career trajectories have been affected by the pandemic an opportunity to request either no cost or funded extensions. We've had a number of these requests. We respond to them quickly, understanding again the vulnerability and the need to allow continuation of careers and career development as we hopefully move through the worst of the pandemic and approach the new normal. Next slide, please. Some additional specific updates next. There's been a realization enhanced even above its prior level in the importance of achieving racial, ethnic diversity, equity, and inclusion. This has taken on many initiatives at NIH overall towards this. The Unite initiative is one illustrated here, which looks at both internal to NIH, external to the research community, communications, other strategies to try to optimize diversification and equity in the research that we support and in the research participants who are an important part of our work. To the right, noted under NIA participation is an illustration of what a leading role NIA has been playing in this NIH-wide event, this including the role of Dr. Marie Bernard, who has been the co-chair of all of Unite, as well as the co-chair of one of those committees, Melissa Espinoza, Michelle Evans, and Patricia Jones, also important in leadership roles. Next, please. NIH issued a new policy on data management and sharing, continuing the emphasis on the value of sharing, a case where I think NIA supported AD/ADR research that, of all of you, has really been a model of trends towards data sharing and openness. These policies were made known, an announcement in January of this year, in October of past year, and become effective in January of 2023. So I look to all of you to be taking the lead as before in conforming to what we've seen as the advantages of open science and data sharing, and our commitment to providing the resources to accomplish that data sharing. Next, please. I want to stress again the activity related to interventions and prevention trials. of great interest to us and certainly to the public as we translate our most basic science into interventions. I want to illustrate here that there's some 270 active trials supported by NIA alone. There's a large number of them, 45 early stage clinical drug development, and notable there is that of the 45, 11 are targeted amyloid, which is one of the early and still remains a very viable target, but the large majority reflect the diversity of targets that have been identified and are now moving into clinical studies. Late stage clinical trials, 123 non-pharmacological interventions. These are targeted at diet, at exercise, at cognitive training, and combinations of all of these. Interventions at neuropsychiatric symptoms, and some 84 that are now care and caregiver interventions, even as we seek to delay or end the trajectories of the disease itself, our responsibility to dealing with the lives and lifestyles of those who are affected and those caring for them, an important part of our overall research mission. Next, please. AMP AD 2.0 was just launched this spring after an enormously successful first iteration, which, as you know, identified some 500 more potential targets for intervention. And I would say set a new standard and a new socialization of the notion of data sharing and open science. Among the emphases now in AMP 2.0, which will bring together some 8 research teams, 20 institutions, and 9 public-private partners, will be a focus on expanding its multi-omic emphasis to include now samples from brain, CSF, and blood from more diverse cohorts than have been the case in the past, and to move towards longitudinal profiling, including that around immune parameters, again, over these diverse populations, expanding the increasingly available single nucleus, single cell molecular profiling to these ends. Next, please. I mentioned the importance of our research directed at dementia care and caregiving. To that end, NIA commissioned a 2-part effort by ARC and national academies to look at published literature on what is known about the effectiveness and evidence for dementia care and caregiving. The first part, carried out by the Agency for Healthcare Research and Quality, ARC, was released last July, but new, at least in terms of the programming of our meetings together, was released in February for the National Academies, of a report that was based on the initial analysis done by ARC and made its recommendations about the status of evidence supporting translations, and most importantly, pointing to research gaps and need for more work in the field. In the next slide, a summary from the National Academies, their key messages. They found that many of the caregiving interventions couldn't be assessed because of the small size, pilot, risk of high bias. And we've learned a lot about the qualities that we are used to in clinical trials and making sure that they are adapted and enforced and respected in these trials as well. And so the new generation of studies already underway has taken seriously the findings from these reviews. 2 types of intervention were demonstrated to be what was categorized as low strength evidence of benefit and particularly worthy of further implementation. This is the collaborative care model and the REACH 2. Next, please. Announcement at NIH, NIA, NINDS joint venture in our intramural program on the Bethesda campus. We've announced before the CARD program, the Center for Alzheimer's and Related Dementias Research, but now the most recent announcement is that of last month, after an extensive search, Andy Singleton was identified as director. The new physical building on campus structure is intended to be occupied next year, but even before that, work has begun, including recruitment to make staff available to leadership with Andy in this program. We're looking at ways to take advantage of some of the unique aspects of the NIH campus overall, the clinical center, the high throughput facilities of NCATS, again, the input of all the intramural programs, with a focus here on, again, openness of science, data sharing, leveraging what goes on elsewhere, and public-private partnerships, as well as academic intramural, extramural partnerships. So another part of the exciting armamentarium we have in confronting AD and ADRD. Next, please. And finally, I want to note the introduction of a new alzheimers.gov website where information about what goes on, NIH, other federally supported efforts, information for the research community, as well as the lay community, those interested in Alzheimer's from their own very personal perspective, and those interested in the prospects for participating, importantly, in Alzheimer's research. Next, please. As noted, we had the recent AD Research Summit. Point out here its existence, in particular the last link, to note that all the presentations have been archived and now available for those who are not unable to watch them or who want to rewatch them at leisure. So there's the link. Next, please. And this is just our usual invitation to please, by proactive or signing on to our blogs as subscribers, let us communicate to you best we can what goes on at NIA to help our partnership together. So I thank you for time for that presentation. We'll move now with my pleasure to introduce to you the Director of the Division of Neuroscience, Eliezer Masliah. Eliezer.
Hi, thank you, Richard, and hello, everybody. Great to see you, at least virtually again, and just to have the opportunity to give you an update as to what is going on in terms of scientific programs through the Division of Neuroscience and how we could best interact with the Alzheimer's centers and enhance the very important role that you all play. So as Dr. Hodes mentioned, we recently had the NIH Alzheimer's Summit, and at the summit there was a great emphasis on developing precision medicine through diversification of the populations, through data sharing, and a number of other resources that have been developed, and all of these in the context of better understanding these rather heterogeneous and also multi-causal disorder on the basis of its genetics, aging, and environmental factors. So I want to tell you a little bit about some of the programs that we've been developing that I think, again, would be of great interest to the Alzheimer's centers. And of course, for many of them, the Alzheimer's centers are very important component. One of them is a ADSP, or Alzheimer's disease sequencing program. And this particular program now has grown considerably. A number of its components have been renewed. And we're now moving toward having more diverse populations in this program. Also, as I mentioned, some of the components of the program have been recently renewed, including the GCAD, and we also recently renewed NIGAS and the ADSP follow-up, which again would include more diverse populations, greater sharing of the data, and greater harmonization of the data. And we recently also had last year our ADSP Global Genetics Meeting in collaboration with the Alzheimer's Association, where the main pathways that have been revealed by the ADSP work, and again, many of the samples of ADSP coming from the Alzheimer's centers, were pathways like APP and presenilin, lipid metabolism, ApoE, neuroinflammation and immune response, synaptic signaling tau, and endocytosis were considerably developed, described, and also how these different pathways are interacting, and the different genetic hubs are also interacting. So we're getting ready to our next meeting that will be in July of 2021, where we're going to move to the next step, which is the question of the understanding of better of the functional genomics aspects of this pathway, the emerging use of biomarkers and clinical research and defining endophenotypes, and also how all of these genetic information might play a role in developing therapeutics and druggable targets. And in this context, the ADSP programs have been developing at least 3 new very important programs, which include a functional genomics program, an artificial intelligence program, and a data harmonization program that, again, I think with the idea of going into the question as to heterogeneity of this disease, endophenotypes, polygenic risk scores, and then hopefully eventually leading to personalized medicine with the core principles, as I mentioned before, as increasing sharing in the data, increasing interoperability between all the different programs that we have, including AMP-AD, with ADSP and our other programs. So I think this is a really very exciting development, and you will be seeing a lot more of these coming up. These awards are going to be made very soon, and we really would like to see this idea of data harmonization and sharing moving forward. Now, another area that also was very important part of the AD Summit, and it has been also a very important theme of our scientific mission at NIA, has been really to promote the idea of aging and the pathogenesis of AD. I know we put a lot of emphasis in the proteinopathy aspects of neurodegeneration, but we often don't think too much about the contribution of aging mechanisms in neurodegeneration in AD, ADRD. So in that context, we have been developing a number of very exciting programs, of which I think many of you are taking advantage of, and includes a neurobiology of stem cells and the context of neurogenesis in aging and AD, ADRD, and we just recently had that RFA out. We have a new RFA coming up now on transposable elements in aging and Alzheimer's disease. These are as a result of a very successful workshop that we had in the topic, and we're particularly interested on DNA damage, DNA repair, and as I said, transposable elements. A very important component of aging in AD, ADRD that has been unexplored is cell senescence, for which we also had recently an RFA, very successful, many excellent applications. And we also had another one on the glial aspects of aging and AD, ADRD. And more recently, and I hope next time I talk to you, I'll tell you more about it, is the cellular scale connectome, which is a follow-up to what the Brain Initiative has been doing, but now applying a lot of that to AD, ADRD. We're really trying to understand better at the systems level, connectivities, pathogenesis of Alzheimer's disease. And regarding the cell senescent RFA and the applications, the kind of questions that we wanted to understand better is what are the defining elements of cell senescence in the nervous system, so like P16, P21, beta-gal, and all the other pro-inflammatory phenotypes that have been described in other places also reproduce, and we need to develop consistent ways of defining this. And also we want to understand better which cells in the nervous system are undergoing cell senescence in AD and ADRD. There has been some work on our intramural program showing that, for example, oligodendroglial cells display cell senescence, but really there are a lot of other questions that need to be answered. I mean, cell senescence of non-neuronal cells, to what extent, I mean, is the chicken and the egg question, does cell senescence contribute to AD or vice versa? The role of targeting cell senescence as a precision medicine approach, and so on. And just to give you some examples, there have been some really very recent publications but this is in the murine brain. Again, there is very little in AD and ADRD brains, and that's where we want to see a lot more research done, but utilizing single cell approaches, which I think is very exciting, showing that both endothelial but also microglial cells, a significant proportion of microglial cells display cell senescent changes. And as I mentioned, I think we don't really know to what extent microglia and other non-neuronal cells in ADRD are displaying cell senescent changes, but there is this recent paper from the group of Pete Nelson showing these dystrophic microglia in ADRD that are very reminiscent to what has been described in other models as senescent cells. So more research on this area, it will be really welcome, very exciting. And I think with the great collection of brains of the Alzheimer's centers, I mean, this is perfect for the kind of work that many of you do. And then finally, another very important component of the summit, which again, understanding the interactions of environment with aging and genetics is quite critical. This was also playing a very important role in terms of understanding development of precision medicine approaches. And I hope I will be able to talk more to you in the next sessions. But in terms of some of the environmental factors, I think given the kind of life we're living now with COVID, infectious etiology of Alzheimer's disease has been quite critical. And actually we reissued as a new RFA our infectious etiology of AD funding opportunity. And we got a number of excellent applications that we'll be funding very soon. And we hope to organize a meeting of the investigators funder on this RFA. We just came up with a new RFA, and you will see that coming up very soon on innate, but also adapted immune responses in ADRD. We had one already on the microbiome, and we reissued or issued a new notice, NOCI, for neuro-COVID. Dr. Hodes has mentioned to you already the supplements, but we also issued now a new NOCI for R01, R21 type of applications. Also, Dr. Hodes has mentioned to you this very exciting new program for trying to understand the post-acute sequelae of SARS-CoV-2 PASC with a special appropriation from Congress over $1 billion to try to answer this question of what is long COVID, how is it characterized. The goal of this program is to really lead to our better understanding of what exactly this post-acute syndrome condition. And there were a couple of different transactional authority, which is a special mechanism within NIH for funding, issued in this regard. We got over 500 applications within a very short period of time. And these would include both individuals with acute and post-acute COVID, including aged, adult, pediatric, and also diverse populations. And the program has both core and in-depth exams, including neurological examinations. So the meta cohort will include a clinical recovery cohort, an autopsy cohort, and an EHR study. And then there will be an investigators consortium and essentially 4 cores: a clinical science, a data source, resource, a biorepository, and an administrating coordinating center. And again, here the idea would be to make all these data available to everybody, also all specimens, blood, saliva, autopsy materials, etc. These awards are going to be announced very soon, probably by the end of this month, and we hope to get started by next by June with this program. And we also have another program going on in collaboration with NHLVI and NINDS, which is called C4R, or Cohort of Cohorts for COVID-19 Research. And many of the programs that you're familiar with, that many of you participate, like ARI, Cardia, Framingham, Jackson Heart Study, MESA, Regards, and so are part of this meta cohort, over 50,000 cases. And with the idea, this is as a meta cohort observational study, also including pulmonary, cardiovascular, but also neurocognitive, and making all these data available to everybody. Certainly what C4R started to do might somewhat be synergistic with what I described that task is going to be doing, and how that is going to be integrated is being worked out. But certainly many of the centers that you work with might overlap with these programs, and I think it'd be important to take advantage of this. And as I mentioned, we now issue this NOC for accepting our type of applications to study neurological and neurocognitive consequences of SARS-CoV-2, understanding mechanisms of pathogenesis, and so on. And we will have the opportunity to hear more about the pathogenesis of SARS-CoV-2, in particular in the context of ADRD and aging, with our next speaker, Dr. Nath, that has some really very exciting data, both from studies that he has performed as well as others. So we look forward to his talk. And following on the environment topic, also we had at the end of last year, this really very exciting meeting on the exposome on ADRD. We had plenary sessions really trying to ask the question of understanding the impact of genetic interactions with the environment and health, as well as the use of mobile health and deep learning. And we're going to hear also more about AI in a few minutes. And we also had a number of sessions trying to answer many of the questions that I was mentioning to you, especially in terms of translation of epidemiology, the role of the microbiome, the impact of air pollution, which seemed to be a topic that is coming back now. So stay tuned. I think we're gonna continue working on this topic, and we're hoping that there would be some new opportunities in this regard. And I just want to close with some new centers that we've been funding in the last couple of years that I think are great opportunities for a lot of the research that you're doing, and also for collaborations with the Alzheimer's Center research. I have mentioned a couple of times before the Center for Alpha-Synuclein Strains at UPenn. But what I would like, and I also mentioned before, the single cell program developed at the Allen Institute by Ed Lane. And again, all the data generated by these centers making available. But I just wanted to mention two new centers that have been formed. One is the next generation translational proteomics in ADRD that actually connects with some very exciting studies on AD proteomics, which I think are perfect for the kind of work that the Alzheimer's centers are doing. And also NAPS, which is our new center to study prodromal synucleinopathies. So in regards to the proteomics center, this is our well-known Tom Montin and Michael McCoss. And this center has 4 projects that seek to really discover proteins that are altered in the CNS using highly quantitative, very reproducible, highly standardized proteomic techniques that we really didn't have before, that can use very small amounts of material. For example, in CSF has been a problem before in terms of proteomic reproducible studies in proteomics, but I think what Tom and Michael are doing is really quite exciting. I think we're going to be getting some excellent data in their regard. And there is also going to be work done in terms of how this correlates with brain mapping. We know that Tom is doing some really very exciting work in this regard. And also they have a project on clinical validation of this work, and also novel reagent development. And all of these data being shared via Panorama, which is a hub, a data hub that has been also developed by programs that are involving NIGMS. So this is really a very exciting development. And as I said, this proteomics center also is a core for other centers in proteomics that we've been developing, or other programs in proteomics that we've been developing. And these ones are, instead of centers focusing on R1 type of applications, or investigator-initiated type of applications, that includes this RFA on structural proteomics, using really the latest on cryo-EM, solid-state NMR, top-down mass spec to study the folding of proteins involving neurodegeneration. This is spatial and functional proteomics, RFA, to really understand at the cell level and in a more topographical specific level, the proteome. I mean, I think we have some general proteome idea, but how does that relate to specific cells, to specific cell regions? And finally, these high resolution brain region cell type small biomolecules mass spec, using all the latest proteomics and mass spec technology that could give resolution at the cell level and a topographic side of molecules, involving even small molecules like drugs and so on, and their binding to specific receptors. Again, these could be quite critical in terms of drug development and understanding of pathogenesis and so on. So three very important programs linking to the whole proteomics effort. And finally, I also wanted to mention this new program, NAPS, to study RBD in as a prodromal synucleinopathy, and develop a large cohort that would enable clinical trials and treatment of synucleinopathies, hopefully using precision medicine approaches. These are the centers that are part of these consortia, and this is an effort also between NIA and NINDS. In many of the programs that I have mentioned to you, we're collaborating with NINDS, and given the time that we have, I won't be able to go over all the protocols that they are building, but they have really very exciting biomarkers, imaging, clinical data, including biofluid DNA, RNA, etc. And this center is a collaborative effort among Washington University, Mayo Clinic, and McGill University. So really generating excellent data, and again, that I think is going to be tremendously useful for the Alzheimer's centers. So I just want to close with a presentation of this certificate of appreciation, and a big thank you to the ADRC Clinical Task Force. We have a number of task force at the ADRC. I know Nina Reeves and the others at the Division of Neuroscience are really doing great work, working together with you. And we hopefully will be presenting other certificates of appreciation to our other task force, this time the clinical task force that include Levy, Andy Saykin, Brad Bovey, Cindy Carson, Greg Hisha, Bobby Rosen, Jeff Burns, Liana Apostolova, Mary Sano, Lisa Barnes, Rhoda O, Sandy Weintraub, Susan Kraft, Susan Schindler, Teresa Gomez Isla, and of course, thanks to NACC, Bob Kago, and Merle Kalan, and to our technology subcommittee volunteers and the data course reps for their absolutely amazing works. Thank you so much for everything you're doing. And with that, I would like to transition to Nina. It needs no introduction. And Nina, please go ahead. Thank you.
Okay, thank you, Dr. Masliah. Terrific presentation. Okay, that's backwards, right? Am I seeing the wrong screen?
Nina, if you want to go to the display settings and do that toggle thing again.
Now I'm not seeing it because the screen sharing is in my way.
Oh, I love it when that happens.
I don't know why it's different now.
Okay. I would do the presentation.
Let me try stop sharing. Nope. Okay, but now I can see it. There we go. Is that better?
You just need to share your screen now.
Oh. Okay, let's try that again. Sorry, folks.
That's all right. You had 2 presentations to toggle. Doing great.
Nope.
So
It's
can you see
changing for some unknown reason.
there, Nina, at where it says display settings with the arrow at the top?
Yeah,
There.
I can't. Is this it?
Yep,
Because
hit
it's not
that.
showing on my screen. There we go. Okay.
Enter view, and there you go.
Okay, sorry about that. All right. So I'm going to move right on into my presentation. My very first slide is something that I feel is important to say. I have posted this comment that was posted on Twitter from Andrea Gilmore Bukowski with her permission. This had a big impact on me, and I saw several others on Twitter. Her comment to use your voice in service of health, Black lives, and justice. And if you haven't already used it, not speaking is speaking for violence and hatred. And so I really took this to heart, and I have a few comments that I would like to share with our community. This situation that we're in, of course, is not new with George Floyd. It's not over with Chauvin's conviction. Systemic racism exists and has existed, and we need to think what we do, what we say, and how we act, and particularly how we don't act when we keep silent. I suggest that we read something, watch something, stretch yourself, rethink assumptions, have uncomfortable conversations like this one, and this applies to all of us. Although we might live and work in bubbles, our research is in a much larger context, and we have to understand the full spectrum of the world we're living and working in so that we can do better science that improves lives for everyone. We can't ask those that are experiencing the greatest impact of these injustices to add to the burden the need to help the rest of us understand their experiences. We have to go out of our way to learn and understand. And when they do share their thoughts, we need to listen, not just hear, but really listen and work hard at being more thoughtful and considerate. Don't put the burden on minoritized persons, and I mean lots of different groups, to be the only ones organizing against injustices. You know what systemic means. It's built into the system. It's built into our assumptions. It got there over many centuries and will take work past our own lifetimes to get rid of it. It won't just go away because we mean well. I commend those of you who have gone out of your way to take major steps toward making positive impacts in your local communities. One example, UC Davis brought in consultants to support the difficult conversations, and they have been kind enough to share the outcomes of this effort. You all should have received that in your email, and if not, we'll get it to you. I recommend you take some time to take a look at it. Many folks provided information, PPE, and volunteers for vaccinations. Some centers are working with federally qualified health centers and others. These are just a few examples. I know many of you are doing great work in these areas. Scientific reviewers are now more often pushing for change. And you see here from Dr. Hodes's presentation about the Unite initiative. I urge you to take a look. at what that involves. NIH and NIA, we're taking a look at ourselves and trying to figure out what we can do to improve things for everyone. Hopefully you heard yesterday that NCRAD is working to increase samples from a broader population. Hopefully you heard the REC presentations and that the REC steering committee has diversity as a major aim. And these and other efforts are going to help us gain a better understanding of the disease and offer new options for treatment. We will be doing better science while at the same time supporting and learning from our friends and colleagues. So I just have a few notes on here, and I want to draw your attention to the point that you can't just bring in one person from a minoritized group and expect them to make a representation of everyone from their group. I want to note also that race is rarely a cause of health disparities, and racism and minoritization have a much larger impact on health. And that many of the folks that are speaking out and helping us to address these concerns, that's not even their area of science. It's not what they're interested in. So we would like to allow them to do their science, their other science, and to consider for yourselves anything further that you can do to help with racism and our other issues that are going on in our community. I just wanted to share with you some of my reading that I've been doing and listening to. I particularly note Jonathan Jackson's Black Lives Matter and Research Too, which was a really impactful presentation that I've listened to. And I'm gonna move on to share some of our successes so far. We have this Asian cohort for Alzheimer's disease, ACAD, led by Lisan Wang, Van Park, and Younga Jun from Boston University, and Helena Chu at USC. If you have further questions or information about this project, you can feel free to reach out to any of them. Also want to welcome, we have welcomed them before. These were funded in September of last year, but this is part of our effort that was started quite a while ago to diversify our Alzheimer's Centers network. And the aim here really was to diversify geographically, which you can see we have succeeded in, and the populations that are being included and the science that's being done. So welcome to our 4 new P20 centers. Again, want to thank the clinical task force. Dr. Masliah presented the certificates of appreciation. And so I just wanted to add my thanks to this group. They've been working extremely hard, and I hope that you will attend the session later, and particularly the breakout room discussions. We left 45 minutes for discussions. They've worked very hard setting up this UDS 4.0, and we really, we and they want your input on where they are planning to go so far. So please be sure to attend those. In our effort to share about what the Alzheimer's centers are accomplishing, we think this is hugely important, and we're working on branding. And I want to express my appreciation to our NIA Office of Communication and Public Liaison. Many staff from the OCPL have been working with us on this, and they're helping to showcase the Alzheimer's centers. You know, of course, this is publicly funded research, and we really want to share it with the public. And so we're going to be amplifying the center's accomplishments through this Twitter handle, NIA funded ADRC. And we ask you to, for those of you who have a Twitter handle, amplify it as well and amplify your research using that hashtag. There was an email sent out to over 60,000 subscribers that is talking about the success of the ADRCs and directing folks where they are. And later this month, they'll begin featuring insights. I think they actually already started on which centers and what they have accomplished. So more to come on that. Again, we are really reaching out and looking for further information. I'm not going to read through the whole slide. These slides will be available, but please do get in touch if you have exciting work to share with the public. As again, part of this communication, I wanted to remind everyone, unfortunately for you, I'm going through your progress reports during the same time we were preparing for this meeting. And I see a lot of you have put these things, not all. So thank you to those that did not put not applicable and nothing to report. But these are important ways that we can summarize the accomplishments of the centers. So I ask you to pay attention to these in the next round of progress reports and share with us what your accomplishments are and what we might be able to share with the public. Here are some of our ideas of what the centers have accomplished. During the pandemic, of course, things have been harder for all of us, but we have been able to get SCAN launched. The Alzheimer's centers played a major role in the AD Summit that was just put on. We have taken advantage of the virtual format by enabling multiple webinars, which are available on the NACC website. Conveniently, the ACTC, the Clinical Trials Consortium, has been interacting more with our Alzheimer's centers, and they had a couple presentations actually on the e-consent form that was developed in collaboration with Emory and Wisconsin ADRCs. As I just mentioned, the communications efforts about ADRCs in the news and the hashtag NIA funded ADRCs, we're ramping up these communications. The REC steering committee has gotten going and have made major efforts on really leveraging the virtual nature of our communications lately. And they're, if you didn't get a chance to hear, planning to work with NACC to share a lot of information on the web so that we can really take advantage of having a network of centers and share our training. And then Cerise presented an inventory of what's available at the centers on biomarkers, and we will be starting up the biomarker steering committee coming in January. So here are all the existing steering committees. And the REC steering committee is green because it's coming soon. And here on the NACC page is a list of our current listservs, and the new NACC staff, Amy Young in particular, is communications expert, and she'll be working on ways to improve our communications. So stay tuned for more on that. Here are some of the webinars, just a few. They're all available on the NACC webpage. But many of the steering committees and cores have put together terrific webinars. As I mentioned, SCAN was launched. It is ready to go, and we have urged you to begin sharing your PET or MRI data from any NACC participant after you get your scanners approved by the SCAN team. Please get in touch with them if you haven't already to make sure that that can run smoothly. We're really looking forward to having more data available in a harmonized way for lots of different researchers. So thank you to those of you who have already started. Wanted to also share with you a Focus on Aging Federal Partners webinar series. And this one coming up on May 20th from 3 to 4:30 Eastern is featuring our Agreed Dementia group, which is an advisory group on risk education for dementia. And they've put together a large number of speakers that we're going to squeeze into this presentation. And I hope that you'll be able to attend, but if not, this will also be archived and available. And the Agreed Dementia website is there for any of you who haven't heard about the group yet. There's a lot going on in that group, and it's open, so anyone who's interested in joining is able to. I want to thank Krista Mulder, who has helped Grayson and me to put together a new iteration of our best practices guidelines. It used to be biospecimen best practices. It was last updated in 2014, and we have put together a large number of groups here to update these and add some new sections. And so some are done, some are still in progress, but now it's beyond just biospecimens, and we'll be working with NACC to add these to the website. And we're hoping that this is going to be more of a living document than before, because obviously all these things are changing very rapidly and it can't be updated every 7 years. It needs to be updated more frequently. So you heard a lot from our other speakers this morning about SARS-CoV-2 opportunities. We know that many of you are starting to give the COVID survey, which we have decided is kind of already out of date. When it was posted last June and worked on obviously prior to that, a lot of things have changed since then. And so we would like more of you to use it, but want to also let you know that we've put together a group, and thank you to Jamie Noble for leading that group. We are going to be announcing this new version, which will take into account many of and concerns and vaccination, which wasn't even available at the time. The previous version, the long COVID and many other factors are being taken into consideration. And I don't yet know if we're gonna make it a requirement, but we're gonna strongly urge folks to use this. So please keep your eye out for that, and we'll be announcing more when it is closer to ready. We have another group that we worked with, being led by Emily Largent at Penn and Rebecca Edelmeyer at the Alzheimer's Association. This really came from a presentation that was at one of the Alzheimer's Center's meetings that was in person, remember that? Where we had people who had participated in a trial that ended suddenly, and they shared with us as a couple their experiences of the trial ending. And several of us thought that that was not okay, what they went through and what others went through. And so we've put together a group, including representatives from academia, industry, stakeholders, trial participants, non-governmental organizations. And they had an inaugural meeting in January, and the next group meeting is planned for July, and they're in the process of organizing subcommittees. So anyone interested in working on this is also welcome to join this group. Just a quick reminder that there was a change. Blood pressure addendum is available on the NACC website. So we got a question about this and wanted to just make sure everyone is aware. There is a list of approved devices there as well with a link. Another effort that I've been personally putting a lot of effort into is a combination of our neuropathology steering committee, the Alzheimer's Center's neuropathologists, and Neurobiobank, which NIA joined in 2018. We've been working with the Brain Donor Project, which is run by Tish Hevel, and she refers people to the Neurobiobank sites. And really trying to help the public to understand. I know that a lot of our centers have gotten calls in the past from people eager to donate their brains, but who don't really understand when they get turned away. And so we've tried to work with, again, our NIA OCPL, the communications office, to share with the public what makes a brain donation most valuable for research. And so we have a number of these posted, as well as we've spoken with the Alzheimer's Association, and they have a newsletter that explains some of this as well. And through these efforts, we've worked with, again, Tish Hevel at the Brain Donor Project to prioritize which cases are coming in. And so this is just as of the end of March. You can see that she refers different people to the 3 pilot project sites of the Alzheimer's centers, which has been, this entire effort has been led by Dirk Keen at the University of Washington. And the second site is Pittsburgh, Julia Kofler. And the third site is Yale with Anita Hutner. And so those 3 sites, they've had 40 referrals since September of 2019 when we first implemented this pilot project. 13 of them were controls, 27 affected. This also impacted the referrals to the neurobiobank sites, where before NIA joined, they were just declining them because they just didn't have the capacity and didn't have a way to prioritize which cases were coming in. So there have been a lot of registrations, partly because of our efforts to share with the public what makes a brain donation valuable. And they have been referring now that they have this prioritization scheme. So this is just to share how that has impacted what the Brain Donor Project has been doing in terms of these referrals. Skip this because we're running late. This is one slide from NACC about future goals. I wanted to just thank NACC. The whole team has been working overtime, I think, to help us prepare for this meeting and think about our future, and they're working on planning. So a lot of good ideas coming up. They're really working hard to make the data submission processes easier and think about how to do this best for the UDS4. And they've been heavily involved in the clinical task force discussions about the UDS4 and working with all of the individual centers to think about what the best ways are for data submission and sharing. And so I hope that you have seen their presentations about the LEAF application. It looks really exciting about ways to access NACC data and visualizations. So stay tuned for more on that. And just my last slide is to share with you that we are currently planning for October in Los Angeles. We're hoping that this can be in person, but obviously we don't know. And we would like to have a good understanding of what the travel restrictions are, what you're expecting in terms of lifting the restrictions. These are the steering committees, and we hope to continue having webinars that really have enabled a lot more inter-core communication, cross-center communication. But of course, we still know the value of in-person meetings, and so hope to get back to that soon. And I'm going to stop sharing. I see that there are a lot of comments and questions, so we're going to have to answer those on the chat in the Q&A. Thanks, everyone.
Thank you very much, Nina. And I really want to thank all of our NIA speakers, Dr. Hodes, Masliah, and Silverberg. Clearly outstanding momentum taking place relative to even the momentum we've seen before. So it's just terrific to see all these programs. I also want to thank Nina for the heartfelt comments with regard to structural racism and diversity issues that are so important. Now it's a great pleasure to transition to 2 science sessions. The first of which will be on COVID-19 related neurologic complications. And we're really fortunate to have Dr. Avindra Nath from the intramural program. He directs the NINDS intramural program, and so a leading physician scientist who focuses on neuroimmunology and retroviral effects, and has done great work on HIV, ALS, MS, and even Alzheimer's disease in his work. But he and his team have led the initial dissection of processes taking place in COVID-19. So it's really a great opportunity for us to hear from him. And Dr. Nath, thank you so much for joining us this morning.
Thanks, Andy, for that very kind introduction. Yes, so my expertise is really in CNS infections. And so wherever you can make a case for it, I'm there, which means that with every pandemic, it becomes, we just add on more stuff on top of whatever else we were doing. So I want to start with this quote here. And this is from Sir William Osler, and he was giving the keynote address to the American Medical Association in 1896. And what he said was that humanity has but three great enemies: fever, famine, and war. And of these, by far the greatest, by far the most terrible, is fever. And that holds true even today. And that all the people who die from famine and war, if you put them together, just pales in front of what happens with infections. In fact, most of human evolution has taken place because you have a, excuse me, a wave of infection comes in, wipes out a huge population of people, and then few survive, and then they repopulate the planet, and then comes another wave of infection and wipes them out. So, so currently we're facing one of the biggest challenges that humans have faced on this planet in a long time. And the challenge is this COVID-19. And you can see here at the time of inauguration of President Biden at the mall, each flag here represents a individual who had died of COVID here within the United States. And there were about 400,000 at least estimated at that time. The total estimated deaths as of today are close to 800,000 people that have died. So in a short time period of about a year, we've had a huge number of deaths just within our own country. 1/10 of the country has been infected with the infection. And at its peak, close to at least 4,000 deaths were taking place per day. About 130 countries so far have not had a single vaccination available to them. And so the global deaths are currently about 3.5 million. It is estimated that by the time we are all done, there will be about close to 100 million people dead on this planet from this infection. So this is the type of infection we have really never faced, and the long-term consequences just cannot be even imagined what they might be. Unfortunately, despite all these pandemics, one after another that piles up here, and the amounts of devastation that occurs in epidemic proportions, and theoretically, these infections could even wipe out the existence of humans on this planet. Our therapeutic options are very, very limited. All we have is antiviral drugs for some of the herpes viruses, some hepatitis, and with HIV, and it really isn't a cure. It just kind of suppresses it. So there are hundreds and thousands of viruses out there, and we have absolutely no therapeutic antivirals for any of them. If you just look at coronaviruses, there are again thousands of coronaviruses, and here I'm just showing you a total of 6, and then the 7th one, coronavirus, SARS-CoV-2. And all human coronaviruses cause neurological complications. Okay. Now, the types of manifestations you see are a little bit different, and they vary depending on the type of receptor they use. But SARS-CoV-2 uses ACE2, so it's quite similar to what happened with the SARS-CoV-1 here. And that's the angiotensin converting enzyme too. The neurological complications can be divided largely into two, but there's an overlap between the two, of course. The first is during the acute phase of the infection, you can get anosmia, you can get an encephalopathy, strokes, you can get a meningitis, seizures. And then there's an interesting phenomenon called Ondine's curse. A number of patients will die suddenly. We think that there may be a brainstem mediated phenomenon in some of them. And then you have these post-viral syndromes. These occur after you recover from the acute phase. We think that most of them are immune mediated, but there are a variety of different manifestations, and I'll go over them in a little bit more detail. And these can be very long lasting, some of them. So I'm going to skip this slide. So acutely, what you do see is that about a third of the patients who are admitted to the hospital have some kind of an altered mental status. Okay. And the consequences of this are huge because the hospital stay is 3 times as long. At the time of discharge, they're unable to manage their activities of daily living. And these neurological manifestations are independent of the severity of respiratory illness. And it's more common in older male individuals. And the mortality rate of these individuals is 6-fold higher. So I think this has huge consequences for the older population, and especially those who are may have some underlying cognitive impairment to begin with. And these patients who are hospitalized, you can, if you do an MRI scan, sometimes you'll see this leukoencephalopathy. And this could very well be due to all kinds of metabolic abnormalities that occur in these patients because they're critically ill. But nonetheless, it's important to recognize that there may be ongoing structural changes in the brain taking place in these patients who are admitted in the intensive care unit, because all the focus is usually on the lungs, and very few people are looking at what's happening to the brain. So one of the questions that remains unanswered is that how does the virus get into the brain, or does it actually enter the brain? And a hypothesis has been that maybe it enters through the olfactory pathways. And the reason for that is that, at least for some of the animal coronaviruses, there is good evidence that you can put it in the nasal cavity and it will go up the olfactory bulb, olfactory nerve into the olfactory bulb, and from there to the brainstem. But with SARS-CoV-2 in humans, it's a different story. You get a lot of replication in the nasal mucosa. However, and you get loss of smell, but it's usually due to infection of the support cells, which are these sustencular cells. And you can see under electron microscopy, you can see these lots of virus, budding off of these cells here. The olfactory nerve itself does not have the ACE2 receptor, and there's no good evidence that it gets infected. This is a study from Germany, and where they found was they claimed that you can find some virus in the olfactory bulb, but most of these individuals, you didn't find anything. And there were only 3 individuals that found something, and that too, it was a very low copy number. So whether this could be just blood contamination, we don't really know. And this is just to show you that the ACE2 receptor is present in the nasal mucosa here, in these sustencular cells. So we did an autopsy of about 30 patients, and a number of them came from the New York Medical Examiner's Office. 11 of these individuals had died suddenly. They were found dead in bed, or they were found dead on a subway. Another person was just playing with his sister, lifting her up and down, and dropped dead. So these individuals were not sick enough to have sought medical attention. And in fact, and their lungs, although they had some pathology, they didn't have, they were not in any kind of respiratory compromise. When we looked at their brains, however, we were very surprised because there was a lot of pathology in the brain. Now, this is the olfactory bulb. We did a high resolution MRI scan on the olfactory bulb. This is an 11 Tesla scanner. And then we homed into areas where we thought there were abnormalities. And what we found was that this green diffuse staining here is fibrinogen. So there's diffusion, a lot of blood products into the parenchyma. And so these large proteins should not be present in the brain. And when we looked at the blood vessels, we saw that they were compromised. So there's decreased staining of these blood vessels here. And we found infiltration of macrophages within the olfactory bulb. So the pictures that I want to paint to you is that there's a lot of vascular injury that occurs in these patients, and that is an important part that is driving the pathology of these in the brain. And you can see large strokes as well. In fact, the strokes are quite interesting. You can see infarcts on both sides of the brain here. So you can get multiple arteries that can get occluded simultaneously. You can get venous and arterial occlusions, and you get multiple organs involved at the same time. So you can get thrombotic events in the kidney, the lung, deep venous thrombosis in the legs with pulmonary embolism, and get strokes. You can also see ischemic as well as hemorrhagic strokes. So you can see a lot of micro hemorrhages over here. And here on some autopsy specimens, you can see here in the cerebellum, there's a micro bleed here. We did MRI scans again of these autopsy tissues, and in some cases you can see these high signal intensity lesions, and under the microscope, these are all inflammatory lesions. Okay. And in some individuals, you can see cerebral venous thrombosis. So, although it's been publicized with the J&J vaccine, you can actually see it with COVID-19 patients themselves. And when you see it in these patients, it's not that you see it predominantly in women. You can see it almost equally in men and women, and they are much older in age than what you would expect from birth control pills or an increased hyperestrogen state. The other interesting thing is that you can see both ischemic and hemorrhagic lesions in the same individual. So this one is taken from the literature. You can see these punctate lesions here suggesting ischemia. And in the same region, you can also see some hemorrhages, microhemorrhages, and you can see inflammation in the walls of the blood vessels. So you can see 3 types of lesions in the same individual at the same time. And so we looked at these, again, autopsy specimens. This is by MRI scan, looking at the pons here. And when we immunostain for fibrinogen, you can see all this brown staining is fibrinogen. And you can see there's just massive leakage of fibrinogen, but most of it is around the blood vessels. So it starts at the blood vessels and then diffuses throughout the brain. And here in the olfactory bulb again, you can see huge amounts of fibrinogen leakage. We looked at the blood vessels further, and and what you could see is that looking for activated platelets, you can see there are a lot of activated platelets in the blood vessels, and some of them get occluded. And this is an interesting blood vessel here. You can see activated blood vessels here, and activated platelets by the endothelium, and some branching blood vessels that are totally occluded. Now, this group from University of Michigan reported prothrombotic autoantibodies in these patients. And so these are directed against phospholipids. But the interesting thing, what they did was they took these proteins and then gave it to animals and showed that they got vascular occlusion, showing that these are really pathogenic in nature. So there are multiple events taking place in these patients. You have endothelial cell damage, you have a prothrombotic state with activated platelets, and you've got autoantibodies that are leading to clot formation. In children, you can get a inflammatory syndrome, and it's called multi-system inflammatory syndrome with COVID. So a lot of the children have not yet been vaccinated, and they've been put back in school. And the fear is that you're going to see an increase in this inflammatory syndrome. And it's going to be quite devastating in children. So it can present acutely with fever, dyspnea, but they can recover from that. And then 2 weeks later, they develop an encephalopathy with the generalized flaccid weakness. If you look at the MRI scan, you can see here in the splenium of the corpus callosum, there's a high signal intensity lesion here. The CSF is usually normal, but you'll find that there is evidence of inflammation peripherally. Multiple organs can get involved, and they will respond to immunotherapies. So it's important to recognize it early and then treat them accordingly. There are many different types of encephalitis that have been described in COVID patients. Interestingly, viral encephalitis is extremely rare. There are only 1 or 2 case reports in the literature where you can actually find virus in the CSF. But when it does occur, it presents like a typical viral encephalitis: neck stiffness, generalized seizures, loss of consciousness. And here you can see a high signal intensity lesion in the temporal lobe. Most often, what they present as is acute disseminated encephalomyelitis. And you can see multiple enhancing lesions within the brain, here in the spinal cord as well. And then there's another relatively rare syndrome that has been reported with COVID, and you can also see it with influenza, and that is called acute necrotizing hemorrhagic encephalopathy. It usually starts in the thalamus. It's bilaterally symmetrical. You'll get hemorrhage along with it, and then it'll gradually spread to the rest of the brain. But it often maintains that symmetry. So the pathophysiology of these things is quite different. Here it's mediated by the virus. ADEM is mediated largely by T cells, and the hemorrhagic encephalopathy is largely mediated by cytokines. Then there's another type of, again, I guess it's a form of ADEM, but is a little bit more indolent. And so these are cases that were reported from Spain. These are patients that were in the ICU for more than 2 months. Okay, and they did MRI scans on them. They had neurological manifestations, and when they found 2 different patterns. One was they found these punctate type lesions within the brain, the first 3 patients over here, and then the last 2 are individuals who had more diffuse white matter changes. They treated all of them with plasma exchange and IV corticosteroids. Interestingly, the first 3 of them responded really well, and the other 2 did not. So the point that they try to make is that these patients who may be even several months out, but if they have punctate white matter lesions, immunotherapy could actually be useful. But if there's significant damage to the brain, it's unlikely to respond. We looked for evidence of neural injury in the brain. We focused on the brainstem because we saw a fair bit of pathology here. So under an 11 Tesla scanner, you can see the beautiful anatomy of the brain. You can see almost every single structure of the brain here, the inferior ology. So we looked at all these nuclei that I've labeled here, are ones we then looked at individually under the microscope. And what we found was that there's a lot of glial cell activation. You can see around the neurons here, a lot of microglial cell activation. So this is immunostaining for CD68. And again, in each of these nuclei, you can see that. But what is interesting to us is that in the pre-Bartzinger complex, and this is where you will, is the respiratory control center. And what I want to remind you again is that these are patients, most of them that had died suddenly, okay? So here we found that there's neuronophagia. So you can see these lymphocytes, macrophages chewing up these neurons here. And you see atrophic neurons in all these areas as well. So suggesting the possibility that there may be a central hypoxia syndrome that may have contributed to their death. So there's a lot of evidence in the literature emerging that there's primarily an activation of the innate immune response, and that's what is driving a lot of these manifestations. So this is a group from Sweden, and what they looked at was neopterin and beta-2 microglobulin, and showed that it was elevated in the spinal fluid of these patients who had neurological complications. They also looked at neurofilament levels and showed that neurofilament levels are elevated, so suggesting that this activation of the innate immune system within the CNS does lead to neural injury. And here, another group in Germany looked at both infiltrating macrophages and microglial cells, and you can see these microglial nodules, and most of them are in perivascular spaces. And you can also see them in the meninges. So there's immune meningitis, and we found very similar observations ourselves. But what we are most worried about is this syndrome that's been called long COVID or long haul COVID. So we think that anywhere from 10 to 30% of individuals at 6 months post-infection are complaining of a variety of neurological symptoms. Okay. You can largely classify them into three groups, but they are overlapping syndromes. The first one is individuals who complain of fatigue, but it's a very interesting type of fatigue that they complain of. It's really exercise intolerant. So the more exercise they do, the worse they get. And even mild amounts of exercise can wipe them out for the entire day. So I remember talking to a cardiologist in New York that developed this syndrome. And since she was a cardiologist, she had everything under the sun that you could probably get investigated. Everything came out negative. But she says that even within our house, she had set up telemedicine on the first floor, on the second floor, and she couldn't take a flight of steps to even get there. And she would get so exhausted, she couldn't even do telemedicine any longer. So then the second group complains of brain fog. And what they mean is really cognitive and neuropsychological manifestations. They complain of difficulty remembering things. And they have a dissociation of time, which is an interesting phenomenon. They can tell you what they ate for breakfast, but they won't be able to tell you whether they ate it today, or was it last week or yesterday. Okay, but the actual event they do remember, they just don't remember when it occurred. And then there's a fair bit of depression, anxiety, and few patients will present with acute psychosis as well. There's one employee at NIH I talked to. This is an older individual who was he never had any psychiatric history and developed COVID, got better. And then he says that he developed these very strong suicidal ideations, and he got scared of himself and admitted himself in the hospital for about a month. And he came out and he was doing well. But he had insight into the phenomenon, which was good. The third set of manifestations are these dysautonomia syndrome. Okay. And this can be very devastating. So I remember talking to a neurologist. She said that she couldn't even sit up in bed. And in fact, even to talk to me, she had to lie down in order to talk to me, because every time she wouldn't sit up, she would get dizzy and she couldn't think properly. These patients may have cardiac arrhythmia. Some will develop hypotension or hypertension, but it's a POTS-like syndrome. And that they will manifest with. And some individuals will have persistent fever, and as well as a variety of different types of pain syndromes. Interestingly, most of it is chest pain, and yet you can't really find anything much wrong with their lungs. The other interesting thing about this phenomenon is that these are not individuals who were admitted in the hospital and very sick with respiratory complications. Most of them recovered at home. They had mild manifestation from the acute infection. Then they're devastated from these chronic manifestations. A number of these things overlap with chronic fatigue syndrome. It may not be the exact same thing, but certainly there is significant overlap between the two. So it's quite possible by studying long haul COVID, we may actually learn something about chronic fatigue syndrome. As you know, NIH is very interested in this. $1.5 billion have now been appropriated by Congress to try and study this phenomenon and to develop treatments for it. I already described some of the autonomic dysfunction that you see in patients with the long haul COVID, but includes the GI tract as well as peripheral vasoconstriction. And this is a paper from Sweden, again, showing you what this autonomic dysfunction looks like in these patients. So the patient stands up, the heart rate goes up, the blood pressure comes down. And in another patient here, there's heart rate goes up, but it's somewhat erratic. And you can see there's a huge difference in the systolic and diastolic pressure when that occurs. People have reported that there is dysfunction in the GABAergic system, and this is by transcranial magnetic stimulation. And I want to caution you. So if you look at this paper, it says it's with fatigue and abnormalities in executive function. So it makes you think that this must be related to chronic fatigue syndrome. But when you look at the paper carefully, you find that all these patients were very, very sick. And, quadriparesis, again, another patient with quadriparesis, and paraplegia. And so these were very, very sick individuals. So it's important to really look at the literature carefully before you jump to conclusions. This is an interesting study that just came out last week. And what they looked at was fluorodeoxyglucose PET scans. And I want to draw your attention to the bottom of the slide, because these are the averages. And so the hot colors here, white and yellow, are where you have increased metabolism. And you can look at the cortical ribbon. In normal individuals, there is really good uptake here. But if you look at these patients with the COVID, and you can see that there's decreased uptake in a symmetrical manner or in the cortex, mainly in the frontal lobes and the temporal lobes here. And this is an interesting study that comes out of the UK, and because of the socialized healthcare system there, they had several 100,000 individuals that they looked at, and they compared them to individuals who had influenza versus COVID, and followed them for 6 months out. And in each case, when they looked at strokes, they looked at dementia, mood and anxiety, all these things were much, much greater in individuals who had COVID infection compared to other types of respiratory infections. Okay, and it keeps going up and up the further out you go, and this is 6 months data. Now, as I had shown you earlier, that macrophage activation seems to be key in this whole process, and this is single cell sequencing from the CSF of individuals with neurological complications. And they identified the cell type, which they call mono2. These are dedifferentiated monocytes, but they are extremely highly active monocytes. Okay, so suggesting macrophage activation. And they compared this to benign intracranial hypertension. Here they compared it to other types of viral encephalitis, and what they found was there's decreased interferon responses and increased T-cell exhaustion in these individuals with COVID. So this is a bad mix, because what it means is that you're impairing the ability to fight the infection because there's T-cell exhaustion, and you have the innate immune responses that are activated. Once you have innate immune responses activated, they don't differentiate very well between the viral antigen and the host. So you got a lot of bystander damage. So it's not surprising that you get all these massive neurological manifestations in these individuals. What we do not know is if they have impaired T-cell activation, is it possible that you may have persistent virus lingering somewhere in the body? And that is a major concern, because that can be seen with a lot of other RNA viruses as well. So what should we do about it? How should we treat these patients? We need antivirals, and we don't have it currently. And I think that's a major problem. We've put all our eggs into one basket, and that is the vaccines, and antivirals have lagged behind. So, but we desperately need them. What about immune modulatory reagents? If there is macrophage activation, we need to suppress it. If there's T-cell exhaustion, we need to reverse the exhaustion. So we need to think about which approach to take, or should we be taking both approaches simultaneously? So this is going to require well-designed clinical trials in order to handle these things. what about the vaccines? So there are a lot of neurological complications being reported with the vaccines that are somewhat similar to what we see with COVID itself. So we've seen several patients with tinnitus, brachial plexitis. I have about 30 patients who have dysautonomia and sensory neuropathy, fasciculations on both sides of the upper extremities, just not the side where you get the vaccine itself. And you've heard about the J&J vaccine related stroke-like manifestations with antibodies to antiplatelet 4. And of course, acutely, you can get the flu-like illness as well. So we have 2 studies ongoing right now at NIH. The first is whereby we'll bring in anybody who has any kind of neurological manifestation from COVID. We would like to understand what the breadth of these complications are. And the second is we are bringing in individuals who have this so-called long COVID type symptoms. And we have had over 400 inquiries now. We screened about 100 individuals with very detailed questionnaires. Our goal is to bring in 50 individuals who overlap with chronic fatigue syndrome and another 50 individuals who have recovered. We admit them for a week and then study them in great detail for virology, immunology, the neuropsych, and all the neurological testing that we could possibly do. And our goal is to then transition them to a platform-based clinical trial with several arms in order to try and treat these patients. So I'll stop here. The few people I want to acknowledge for the neuropathology part of the study that I showed you here. And that is, most of the brains that we got were from Rebecca Folkert at New York Medical Examiner's Office. We got a few from Marco Hefty at University of Iowa. And Daniel Pearl was instrumental in helping us make all this happen and looked at all our slides. And Dr. Masliah was also key in helping us through this process. These are the people in my lab who did most of the work. And Dragan Merrick runs a core facility. He did all the fluorescent immunostaining. And then Alan Koretsky and Govind, they did all the MRI scanning for us. They had provided us access to the 11 Tesla and the 7 Tesla scanner. And Walter Korschetz is our institute director, and he's been very supportive of the studies that we are doing. So I'll stop here.
Dr. Nath, thank you so much. The topic could not be more timely, and it's so important for all of us to get a better understanding of mechanisms and clinical manifestations. Greatly appreciate your joining us, and I know you have another Zoom that you're juggling near simultaneously, and we're running a bit behind. So rather than taking questions, we'll go on. But our sincere gratitude for your talk and joining.
Thank you for having me here.
So we're now going to turn our attention to another very timely topic, which is the application of artificial intelligence to Alzheimer's disease research. We have two speakers. First is Jason Moore. Dr. Moore is the Edward Rose Professor of Informatics at the University of Pennsylvania and Director of the Institute for Biomedical Informatics and also Associate Dean for Informatics, and is a visionary thinker, as you'll see in a moment, who I've been inspired by over the years. And I'll just give you one example. Back some time ago, when the whole field was preoccupied with genetics, looking at one SNP at a time, Jason's website was called epistasis.org. I think it still is. And it's been focusing on gene-gene interactions for a long time and much more. So he's been thinking a great deal about these issues and their application to medicine. So let me get right to Dr. Moore, who I know also has another panel right after this. Jason.
Great, thanks, Andy. I appreciate the opportunity to speak to this group, and I'll try to move quickly because I know we're behind schedule and I want to leave time for the last speaker. So as Andy said, I've been working in the artificial intelligence and machine learning space my entire career, and developing novel methods and applying them to biomedical problems, including Alzheimer's disease. So I approach human health very much as a complex adaptive system. This slide gives an overview of the features of complex systems. And the most important one is that the emergent behavior coming out of a complex system cannot be simply inferred from the behavior of the components. And so at the bottom of the slide, we have the many components of a system. We can think of these as genes, proteins, environmental factors, et cetera, the kinds of things we think of as biomarkers for Alzheimer's and other related diseases. And those components then interact with each other to form units. Units interact with each other to form control structures. Control structures, you can think of a control structure as a biochemical pathway, for example. The control structures interact in a system, and the output of the system is the thing that you're interested in this case, measures of human health. And the point again is that it's difficult to predict health from knowledge of the individual components. And we see that with GWAS, for example. GWAS results give us a lot of hits, give us a lot of components, but those individual components don't do a very good job of predicting risk in things like polygenic risk scores. And so we can think about brain health also as a very complex system. And so component might be something like a lipid metabolism gene. A unit might be the regulation of the gene, all the things that go into the gene regulation. And then a control structure might be something like lipid metabolism. And so we can ask ourselves, where does this complexity come from? And the Alzheimer community has been struggling with this for many years, the vast complexity of the disease and the vast complexity of brain health. Well, evolution has one idea for where that complexity comes from. And the basic idea is that evolution has worked to shape the human brain through stabilizing selection. In other words, it's trying to stabilize the phenotypes of the human brain so that we can live, we can function, we can reproduce, et cetera. And the way that evolution shapes brain health is through something called canalization, which is basically creating robust pathways, robust systems that make up brain health such that they're resilient to the effects of mutations and environmental perturbation. So a phenotype is said to be canalized if it's resilient to mutations and environmental factors. And I very much think the human brain is very much canalized. And I think we see that in the complexity of Alzheimer's disease and the pathways underlying it. And so even taking something like lipid metabolism, which is one of many components of brain health, lipid metabolism in the brain is incredibly complex, many interacting pieces and parts as displayed in this picture. And it's amazing on the left side of this figure, which comes from a Frontiers in Physiology article a few years ago. On the left side are all the various things that can perturb lipid metabolism. And when you look at this long list of things and think about all the things that it can affect lipid metabolism, it's amazing that we are actually able to function with healthy brains. And the reason that these things don't perturb lipid metabolism in a big way is because I believe lipid metabolism is canalized, that evolution has stabilized this phenotype to give us brain health. And what we observe of disease, of course, is the disruption of this system, the accumulation of many mutations, knocking out in a synergistic manner different parts of these systems along with environmental perturbations. And that's what ultimately drives us out of that healthy range toward a disease like Alzheimer's disease. Now, we live in an exciting time, and many of you are collecting multimodal big data on patients and healthy subjects. And it's an exciting time, especially for me as an informatician, to have access to all of this data, and kudos to this group for making all that data publicly available so that we can get access to it and work with it. And when you put big data like that together in the context of a complex system, it's a very daunting task, as all of you are struggling with, to make sense of these various components and how they affect brain health. And I think artificial intelligence is absolutely essential for making sense of this. And so I'm just going to run through a list of my AI recommendations, and I'm going to give you a quick example of something that we've worked on. And I've worked in a whole bunch of these areas, so I think all of these are very important, and I'm sure we could add to this list. But I'm a big believer that we need to be incorporating biological knowledge into AI because we don't ignore the biological literature when we do a scientific study. Why should the AI ignore everything that we know and everything that's in the literature? And as such, when we work together in collaborative teams to solve problems, and I think why should the AI be working in isolation? I think humans should be interacting with AI, giving feedback, giving ideas, playing, and the AI and the human should be playing off of each other. So I think this is a very important area where we should be focusing on. Of course, AI software should be open source. It should be transparent so we know exactly what the software is doing so we can trust it. Answer the why question. You know, expert systems in the early 1970s were a type of AI, and you could push a button and say, why? Why did you give me this answer? And the computer could backtrack and tell you why. Modern AI systems can't do that. You can't tell that of a deep learning algorithm. You can't say why and have the deep learning algorithm tell you, well, this model works because of this, this, and this. And so this is an area we need to put a lot of emphasis on. Of course, interpretation is a big one. We need interpretable models. And importantly, actionable models. Drug development in the Alzheimer's space is so very important. So we need AI that generates models that we can take back to do experiments on, to validate drug targets, et cetera. Trustworthy. We need to be able to trust these algorithms. We need our AI systems to have a memory, to learn from experience, to have access to every analysis that's been done and every result that's been generated. We need these results to be transferable to other types of problems. We need our AI algorithms to be energy efficient. We need them to be fair and unbiased. We know that healthcare data is very biased, as Nina touched on the very important issues of structural racism earlier, and that finds its way into the data that we collect. And the algorithms exploit those differences in ways that are detrimental to one group or another. And the one I'm going to focus on for the rest of my presentation is I believe that AI should be accessible and easy. Every single person that wants to use AI to look at data should be able to do so and do so easily. And that's really been one of the goals of my research program over the last 6 or 7 years is how can we make AI easy and accessible so that everybody can use it for their Alzheimer research, regardless of their experience or expertise. And so why artificial intelligence? And I'm deeply interested in how we as humans make decisions about data analytics. If I was to give a Alzheimer data set to everybody on this call and say, let's come back in a week, you can do any analysis you want to do, we'll compare notes. Each of us would take a different path through that data set based on our training, our experience, our expertise, based on what worked and what didn't work in previous analyses. We would feel our way through the data. We would try different things based on our background, and each of us would take a different path through that data set. And so the fundamental question I'm interested in this work is, can we get a computer to do that? Can we get a computer to tinker with the data, feel its way through it, learn from experience, get better with time, and automatically do an analysis as a human would? And so we started out about 4 years ago to develop a system that could do this. And it's what we call Pen AI, which has these components. And I'm just going to go through these very quickly, given the limited time. The first thing we needed was a set of machine learning code, and we used the Scikit-learn library, which is an open source Python-based machine learning library. We needed a controller. We needed a way for the AI to be able to launch analyses, get results back, and do something with them. We found an open source controller that we adopted. And then we needed a database. I talked about memory. For an AI needs a memory of everything it's done before so it can learn from experience. And that's really key to Pen AI. And so we adopted MongoDB, which is a type of database called a document store. So the controller grabs a data set, grabs a machine learning algorithm, runs an analysis on the server, deposits the results in the graph database in MongoDB. And then those results are there with all the metadata so that the AI can then use that and learn from it. And then we designed an AI algorithm that can learn from experience, that looks at the database, looks at the history of results, and then determines for any particular data set what the best machine learning algorithm and parameter settings are to run. And then it can do that automatically without human intervention. And then we needed a way to visualize the results and an interface. And that's what I'm going to show you next. So when you log into Pen AI, this is what you see. You log in through a web browser. PenAI runs on your server, not our server. So you install this, it's open source. You install this on your own server behind your own firewall in your own secure location. And when you log in, each box here is a different data set. It shows you the best result, machine learning result found thus far. So for this first data set, there are 46 machine learning results in the database. And then you can run a machine learning analysis in two different ways. So if you push the AI button here, the AI takes over and starts launching automatically what it thinks are the best machine learning analyses for your data set. And so this is so easy, a 2-year-old can do it. Anybody on this call can do machine learning on Alzheimer data with this tool. You load your data as a CSV file, you push that button, and you're doing machine learning. Now, you can also do a manual analysis by pushing this blue button, and we have simplified this. We have some commonly used preset machine learning algorithms for both classification and regression. You click on a method like a decision tree. We have a preset number of parameters here. You pick the parameters and hit go, and the machine learning analysis runs. The result goes in the database. Now you're doing machine learning. You're contributing to the knowledge base of the AI, and the AI can learn not only from its own experience, but from your experience as well. But you can see how easy it is to do machine learning with this. You're literally pushing a few buttons and you're doing machine learning. The results are then showed in a table. So these are all the results for a particular data set. You can sort them by accuracy. You can see the different algorithms. Now you can click on this button and you can do two things. You can download the model and you can download the computer code. So it writes the Python code for you. So there's full transparency. You can see exactly what PenAI is doing. You can also drill in and look at the parameter settings, et cetera. And if you click on one of these rows, we have a nice dashboard that summarizes all the performance metrics, the confusion matrix, the ROC curve with a 95% confidence interval. And we have several different tools in here for interpretation. One of them is permutation feature importance scores, where we randomize each variable one at a time, look at the change in performance, and that gives you an idea of what your most important variables or features are in the machine learning model. I don't have time to go through this, but we just published a paper in Bioinformatics putting this to the test. We presented PenAI with hundreds of individual data sets and watched how it learned over time. And we tried different algorithms behind the AI for learning the patterns that are in the database and making the recommendations. This is what's called a recommender system. It's kind of like when you go shopping on Amazon and Amazon is recommending things for you to buy. PenAI is recommending the next machine learning algorithm to run. And we can see after a small number of data sets, the performance of PenAI is improving dramatically compared to an average recommender or a random recommender here at the top. So this convinced us that PenAI was learning. We compared it to some other state-of-the-art automated machine learning tools and showed that it was performed competitively with the best out there. And we didn't set out to develop the most powerful automated machine learning tool. We set out to develop the most user-friendly, and it just so happens it's also one of the most powerful. One of the first real data analyses we did, we took this data set, which is from a large critical care database of 60,000 ICU patients, and used it to predict septic shock. This was a study that somebody did where they developed a fancy deep learning algorithm for predicting septic shock in this electronic health record data. And we let PenAI automatically generate models. We also had a naive user. This was an undergraduate student who didn't know anything about machine learning. We let them run 5 analyses as kind of a naive user experience. And in less than an hour, PenAI found a gradient boosting model with a testing accuracy on the holdout data of 0.85 that was statistically the same as what the deep learning algorithm that the authors of this paper had published. And the deep learning algorithm took 30 hours to run. PenAI took less than an hour to run, automatically found a model that was competitive. So the software is freely available. It's open source. It's on GitHub, and it does come installed in several Docker containers. So that's the only challenge, is you have to have Docker installed on your server. This will run on your laptop as well with smaller data sets. You can try it out, but you have to install Docker first. That's the only complication. But let me know if you are interested in collaborating, if you need help, if you want to develop new algorithms for PenAI. We'd love to collaborate with you. And I'll stop there. I want to acknowledge the team that helped me put together PenAI. Wei Shan's a programmer. Bill Akava was a postdoc who just got a faculty position at Harvard. He developed the AI recommender system. Michael Stauffer developed the interface. Heather Williams, the project software engineer that really orchestrated the entire project and how all the pieces and parts fit together. This was an infrastructure project that was funded by the University of Pennsylvania. So we're rolling this out to our health system for user-friendly automated machine learning on healthcare data in our health system. So we're scaling this up right now. This is my email address. Feel free to reach out to me. I know this was a short talk, but I'd be happy to schedule a longer version of this at your institution. If you're interested, let me know, or if you have questions, email me. And as Andy mentioned, my webpage is epistasis.org. I'm on Twitter, very active. And if you follow me, I'll try to follow you back. And Andy, I'll stop there, and hopefully we have time left for the next speaker.
That's fantastic. Thank you so much, Jason. It's always really inspiring. I don't see any questions, and we are a bit behind time. So I think, and I know you're on another panel shortly. So I suspect people will take you up on your generous offer, whether it's to download software to pull you in for a longer talk. I think I will as well. Anyway, thank you so much, Jason. Our next speaker, I think this will be a very nice segue, is Duygy Tosun-Turgut from University of California, San Francisco. Duygy is a biomedical engineer and directs the medical informatics, medical imaging informatics and artificial intelligence program at UCSF, as well as the Center for Imaging and Neurodegenerative Disease. And Duygy, as many of you know, is highly active in many Alzheimer's disease projects. It's a key player, COI in ADNI, in a number of other projects, including AI for AD-U01 connected to the Alzheimer's disease sequencing program, and also integrative work looking at harmonization across ADNI, ABLE, several WashU cohorts, and more. So she's right in the middle of all of this, and I'll stop and turn things over to you, Duygy. Thank you for joining us.
Thank you so much for the invitation, and then you kind of summarized my talk very nicely, actually. My talk going to be very focused on imaging specific challenges and the role of AI, but I want to echo some of the things Dr. Moore highlighted. I'm a true believer of domain-specific knowledge and also multidisciplinary integration to make AI really useful for neurodegenerative diseases, for Alzheimer's disease. So this is actually what we see when we look at the timeline of the dementia research historically. It's a very old concept. Dementia is a very old concept, and as medical technology improved, our ability to look at biochemistry, our knowledge on genetics, our understanding of the dementia and its causes is also improved. And around our late 1990s, we seen this huge improvement in brain imaging, neuroimaging, and at that point, we actually started to see an influx of neuroimaging studies, which greatly contributed to our biological understanding of pathophysiological processes underlying Alzheimer's disease and related dementias. Sorry. Oops. Sorry, I'm just gonna start it again because that's my bad. Try this again if this works. Okay. So as a result, there's thousands of studies that's been published using different neuroimaging techniques, looking at different aspects of brain changes and pathology. And this had led to reach what I call neuroimaging portfolio seen in many neuroimaging initiatives nowadays. That ranges from structural imaging, from MR imaging modalities, as well as functional and molecular imaging modalities like amyloid, tau PET, FDG PET, and many, many more we're exploring nowadays. Although each modality contributes to our understanding of the disease process from both structural and functional perspective, among all these, I will say amyloid, tau PET imaging, structural MRI, and to some extent FDG PET have especially played a very significant role in many clinical research studies and clinical trials. And one of the key game changers was the biological definition of Alzheimer's disease under the NIA and Alzheimer Association research framework. We now see a big shift from syndromal disease definition to a biological construct where Alzheimer's disease continuum is now defined by imaging biomarkers of particularly amyloid, tau, and neurodegeneration, which could be from structural imaging or from FDG PET or other fluid biomarkers. So we are really already witnessing how the biomarkers enable the research community to better communicate in a common language. So the hope is to facilitate identification of risk factors for Alzheimer's disease with greater precision, construct new AD conceptual models, and also accelerate the drug discovery. But at the same time, it's clear that we live in a quite interesting time of abundant data. If we think about data science and the use of data to learn from, perhaps it's a little bit high, the emphasis we put on AI, machine learning, or deep learning. But on the other hand, there's enormous potential now with the data science techniques to find relationships between this really high dimensional data, high multidisciplinary data sets to relevant clinical outcomes. And this impact has been a great interest from different perspectives. So as in many other domains, we are already seeing the adoption of artificial intelligence, deep learning, or machine learning. I'm going to use those terms interchangeably. So we're seeing the impact of deep learning in imaging neurodegenerative diseases, and that is ranging from applications for faster or safer data acquisition or reconstruction to using deep learning or AI for post-processing for phenotype extraction or analytics, to using deep learning to enhance complex data interpretation for diagnosis, for prognosis, or treatment stratification. We're also seeing the use of deep learning applications on pre-imaging workup, like when a certain acquisition might be important in a given context, in a clinical context. And there's definitely other areas, what I tend to call them as the contextual deep learning, where the deep learning approaches tries to touch on multiple aspects of this workflow, from data collection all the way to treatment stratification. So the rest of the talk, I'm gonna try to touch a couple examples from this workflow, not all of them, but I think that the ones that might be quite relevant to ongoing clinical trials particularly. So I want to go back to this, the recently proposed biological definition of Alzheimer's disease, and the effective implementation of such biological construct requires availability of biomarkers. And there's a huge list of options how we can get these biomarker information. So on one hand, imaging biomarkers for the first time allow us for in vivo assessment of neuropathology, also allow us to better understand the etiology of each individual's clinical symptom. it's also allowing us to model the pathophysiological changes at a very high accuracy, but there's a cost that comes with it. Basically, like neuroimaging, particularly molecular neuroimaging, is very costly, it's inefficient, it's not scalable. And furthermore, when we think about particularly molecular imaging, it requires a molecularly specific acquisition that could be not just invasive or sparse in terms of distribution, but also it could put lots of additional burden on the patient, as well as exposing the patients for more radiation. So one of the questions in data science or in AI domain that's been asked is, how can we make some of these acquisitions faster and safer without actually compromising any imaging quality? So the convolutional neural networks have been quite attractive to perform what we call super resolution neuroimaging, which is a framework that could be leveraged for shorter scan times, or in this example, for what we call ultra low dose diagnostic. So this is a great study from Dr. Zaharchek's group from Stanford. And this is an example of a positive amyloid PET image acquired at PET-MR scanner using only 0.24 millicurie of tracer, which is roughly like the 3% of the usual standard dose. And what they've been able to show through a deep learning model is an encoder-decoder approach using different MR acquisition together with a very low dose PET acquisition to synthesize a full dose PET image. And they were able to show that the synthesized image have a similar image quality compared to 100% dose injection image. And so from Alzheimer's disease perspective, the potential impact for improved patient safety is unquestionable. And also, as Alzheimer's studies are moving toward cognitively normal in younger participants, reducing the dose would be helpful. Furthermore, tracer costs could be reduced if doses can be shared. And this is particularly of great interest given the importance of amyloid phenotyping in Alzheimer's disease for effective delivery of amyloid targeted therapies. Screening patients for amyloid burden will be the key. And at the same time, there's a great interest to screen patients for the trajectory of their amyloid burden. So this was one of the questions we were trying to tackle in this recent study. We applied deep learning to predict amyloid burden, not at the time of imaging, but also in upcoming years to capture the disease prognosis. And this is a hybrid enforced learning architecture used to predict amyloid status directly while measuring the SUVR burden as a regression model. And we leverage more than 2,500 cases from AMI study. And we were able to show that even predicting the upcoming amyloid accumulation rates is quite possible with these deep learning approaches, which are also biologically meaningful when we look at what we call the relevance maps that drives the underlying architecture. So similarly, to better define the Alzheimer's biology, this is the work from Andy's group. There have been approaches to develop deep learning models on other PET images. In this case, it was the tau PET imaging to identify the regions and the signals in the images that are best to diagnose people with Alzheimer's disease. And obviously, these data-driven signatures are quite consistent with what with the familiar signatures we used to see from from cohort analysis. So this is another encouraging improvement or advancement in machine learning or data science, where we start to see the biologically meaningful models coming out from these data-driven approaches. So another area where AI is very useful is for identifying pathology, but actually without the need for expensive or invasive PET scans. And this is, many of us have been seeking the best combination of genetic, blood testing, or MR imaging together with cognitive or clinical measures to do amyloid phenotyping. And in a recent review paper, we actually identified more than 200 proposed machine learning methods to stratify individuals as amyloid positive or negative, but not using CSF or PET imaging data. And we also had our fair contribution to this huge list of models, proposed models, and in an earlier structural MR-based modeling study we did, we proposed for MCIs, and we show that if information used from the entire MR image, not limiting to hippocampus or AD implicated regions, there's a good chance of doing amyloid phenotyping with a very high accuracy and good sensitivity and specificity, and it actually outperforms clinical information, the value of clinical information in hippocampal volume. We extended this model to multimodal approaches, showing the added value of, for instance, the perfusion together with structure, particularly in early stages of the disease. But I think most important finding from some of these studies was when we look at retrospectively the clinical trial data from Lilly's expedition study, we illustrated that the differential trajectory of clinical decline is detectable independent of the method used to do amyloid phenotyping, meaning using PET imaging versus using this AI-informed amyloid phenotyping, we still see the same, we can still capture the same clinical trajectory differences. And this has a great importance, particularly in the context of mixed or comorbid non-AD pathologies. And this is a very busy slide, but the main thing I want to highlight is comorbid age-related neuropathologies are highly prevalent, and pathological AD accounts for a considerable percentage of Alzheimer's dementia cases and also variance in cognitive decline. But multiple other pathologies also contribute significantly to their cognitive symptoms, like TDP-43, Lewy bodies, vascular pathology, CAA. And the degree to which Alzheimer pathology contributes to cognitive decline varies greatly from person to person, depending on which other comorbid non-AD pathologies are present. And this also has implications for the development of therapy targets and the stratification of patient cohorts for therapy trials. And unfortunately, molecular biomarkers like from PET imaging or CSF or even blood assays currently exist only for amyloid and tau, and we're still lacking biomarkers for these non-AD pathologies. So this is an ongoing research we're pursuing, but in a recent study, we developed machine learning models, deep learning models based on, again, structural MR imaging, which is widely available, routinely collected, together with information about the participant from demographics and clinical perspective, and amyloid and tau phenotyping information from currently available biomarkers. And the goal was to decide whether the person whether individual has different types of non-AD pathologies that will never really be visible, only at postmortem. And training this on autopsy confirmed data, particularly from NACC data, many of the ADRC sites has been contributing to that, as well as the annual autopsy cohort. that allowed us these subtypes to be identified via a data analytical tool rather than a new molecular imaging modality. And this could be used to identify subgroups of people in a drug trial for stratification or enrichment, or also to identify the risk factors. And this could also contribute to our understanding of the trajectories of cognitive decline of individuals with and without mixed pathologies or comorbid pathologies. I would like to end my talk with a slightly different topic, and this is really about the big data. That big data is really the key ingredient in many of these deep learning approaches. So most of the time in neuroimaging, we have large dimensionality more than big data. So multi-site recruitment and leveraging multiple imaging studies have facilitated some of these deep learning developments in Alzheimer's disease and other neurodegenerative diseases. And this is actually brings the challenge of data harmonization. And the time component also is an added layer of complexity in terms of data standardization and harmonization, because as the relatively slow progressing, if we consider the relatively slow progressing character of the Alzheimer's disease particularly, some of the research studies on neurodegenerative diseases require long follow-up times, and during which we see many technical improvements, technical upgrades. And those are really inevitable. It's important for our advancement, but so it adds to that complexity of heterogeneous data collection. And one repeatedly asked question lately is in data harmonization community particularly is, how would someone's brain look if you've been scanning, if that individual's been scanning different scanners? So that's the underlying question in many of the data harmonization approaches out there. And we're actually seeing many different approaches ranging from post-statistical harmonization to really trying to enforce standard acquisition protocols, to going back to the raw data and understanding what contributes to that raw data's heterogeneity, and try to remove that heterogeneity that comes from imaging tools or the scanners. And from that perspective, we're actually seeing some extremely innovative approaches developed in this domain. And this is one example from Paul Thompson's group at USC, where they use deep learning and adversarial networks to do inter-converge data across scanners. And the variational autoencoders maps the data into a scanner, what we call a scanner invariant latent space. That's the true biology, true anatomy of the brain we want to capture, independent of the scanner or the protocol properties. And similarly, one ongoing challenge from that perspective is how to teach the machine or the algorithm to differentiate between the acquisition related variants versus biological variants. Because at the end of the day, we really want to preserve information about the disease and the biology. And this idea of differential learning about the content and the style of the spaces that describes the anatomy versus the scanners or the protocols was nicely illustrated by this work from Neda Jahatsan, again from USC. And what you're seeing here is on the top row, different images from different protocols. And the left column, a new images coming from unseen cases. And on the bottom row, as we get a new acquisition type, the top row images are actually harmonized to this new acquisition property or the protocol type. without changing the anatomy, without changing the biology, but really just adjusting the underlying domain of scanners or protocols. So just coming back to what Dr. Moore also said, to truly study the Alzheimer's disease, it's absolutely important to consider neuroimaging in the context of data from other disciplines. That's genomics, that's proteomics, that's variable data, cognitive data, clinical data. And I like to actually acknowledge the AI for AD initiative, which is a newly funded collaborative project by NIA, applying artificial intelligence and machine learning to accelerate diagnosis and drug discovery and precision medicine in Alzheimer's disease and related disorders. It's a big effort, including 11 different sites, and some of the key, the PIs and some of the key investigators, site investigators are shown here. And some of the work I tried to summarize in previous slides are actually coming from this AI for AD initiative. And there's one AI application I actually want to quickly highlight. This is by Li Shen, one of the PIs of the AI for AD initiative. And so deep learning can find patterns in brain images that are associated with sets of markers in the genome with omics data. And in this work, Li Shen combines combines by Informatics database on druggable pathways and genetic pathways with, it's a very sophisticated deep learning method, the deep CCA approach that will find combinations of markers and motifs in genome that best predicts the subtypes of dementia in the images. And this obviously is a very attractive area where the disciplines are considered, information from different disciplines are co-analyzed to better model the underlying disease pathophysiology. There are many various applications of deep learning in imaging of neurodegenerative diseases. It's very hard to capture all the recent high impact developments in this talk. Unfortunately, I tried to give a couple examples from our efforts. And one common theme in many of these applications is really leveraging hidden information in multimodal imaging. And there's still plenty of opportunities for deep learning to make an impact in clinical translation and contextual prediction models, and also population-based imaging AI, which is usually not the focus, are the two domains that are potentially very important for an impact for AI. And so the one big question is, how can we identify imaging information that is not immediately important at that time, but carries prognostic value for knowledge learned from population data, but driven by the individual's data at a time in their disease progression. We're of course facing many ongoing challenges. Bridging disciplines is probably more important than ever when we talk about application of AI in Alzheimer's disease. And also in other domains, high cost of validating some of these deep learning models for generalizability. It's still a big challenge, and this is where data sharing and efforts on harmonization and standardization plays a big role. So we can properly test the actual generalizable, scalable value of some of these data analytical approaches. And thank you for your attention, and thanks again for inviting me. And I'd be super happy to answer any questions, or if you want to reach out to me directly for any suggestions, any questions, I'd be happy to answer those as well.
Wonderful. Duygy, thank you so much. We have a hard stop, I guess, for this session. and an award to announce. I'd like to just once more thank our speakers for a fantastic set of very inspiring talks and very informative information. I'm sure many of you will want to follow up with them. Now I'd like to turn to the 2021 ADRC Research Education Component Rising Star Awards. There are 2 awardees, since we have a virtual envelope here, I'll just go ahead and open it. And our 2, first of all, they were all fantastic. I heard most of them, and they were just great to see all these terrific young scientists. However, these 2 were singled out by voting for special recognition as the Rising Star awardees. Valentina Gisay, I apologize if I'm mispronouncing, plasma A beta 42/40 ratios in cognitively unimpaired late middle-aged and older adults, ApoE, E4 homozygotes, heterozygotes, and non-carriers. And then Anna Doherty from Michigan, iron-related oxidative damage and Alzheimer's disease and related dementia. Congratulations to both Rising Star awardees and to all of the other REC representatives from all the centers who gave terrific talks. And that closes the director's session. Thank you all very much for your attention, and looking forward to the clinical cores and other talks this afternoon. Thank you very much.